The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next speaker is Seth Roswurm on behavior of type K shrinkage compensating concrete under various forms of mechanical restraint. He's graduated with his Master's of Science just this last May. He's presently pursuing his master's degree in this topic, and this is actually before his defense, so please be gentle. Thank you.
Well, as Dr. Ramsey said, I'm Seth Roswurm. I'm going to be presenting on behavior of type K shrinkage comp under various forms of mechanical restraint. First of all, I'd like to thank a few people at the University of Oklahoma and Fierce Structural Engineering Laboratory. This is a facility where this research was performed. My advisor is Dr. Chris Ramsey, and the sponsor for this project is CTS Cement Manufacturing. Here's a quick look at the topics that I'm going to cover today. First of all, background and theory, a little bit of the motivation that sort of drove this project, method, why it was performed, how it was performed, quick look at the results and the observations that we made, and then conclusions. So as a sort of background introduction to the topic, a little bit of why I studied what I did is basically concerning constraint of slabs on ground. And this is handled some by ACI 223, the American Concrete Institute specification for shrinkage comp, as I'm sure most of you are familiar with. And there's some language in the specification that concerns the situation where a slab on ground will be cast and is surrounded on all sides by mature concrete, or concrete that is more mature. And about that situation, the specification makes the following statements. Basically, slab on ground surrounded by existing will have infinite restraint. The specification says there can be no movement, and the situation will result in high compressive stress, but may provide little compensation. So in other words, you will induce a stress because of the material expansion, but will not achieve displacement. So here's the scenario that I'm talking about. As you can see, this space has been prepared for a shrinkage comp slab to be cast, and it's surrounded on all sides by concrete that has mature properties, that is, mature stiffness, mature strength, and dimensionally stable, i.e. no longer desiccating or expanding. Here's a schematic of that scenario. In profile view, the expansive slab is shown in the center. It's bounded on either side by slabs of mature properties, and when the slab begins to expand, those adjacent slabs will exert reaction forces against it. And about this situation, shown at bottom, ACI 223 specification says sigma equals P over A. Compressive stress will result, but any compensation or displacement due to mechanical and material effects will be approximately zero in this situation of constraint. So this is shown on the photograph. Red arrows indicate reaction forces. Black arrows indicate the action of the expansive slab. So the question that fundamentally arises from this discussion and this 223 handling of restraint is, does total restraint truly exist? Classical mechanics would indicate that it can't exist because a perfect boundary condition is a theoretical construct and may not be able to exist in reality. According to Hooke's law, force always accompanies a displacement. If a force is applied, material should displace, especially if the boundary condition is being exerted not by a theoretical construct, but by an actual concrete slab. Concrete is elastic over a small range, so when it's loaded, it should be able to respond in an elastic manner. So concrete should not be able to truly exert a perfect boundary condition. Here's a quick schematic showing elastic behavior of concrete under load. Shown at right is the unloaded condition. A concrete specimen of length L is loaded. At left, it displaces with a change of length delta, leaving a final length of L minus delta. In a similar manner, a steel rod is shown here. At right is the unloaded condition. At left, it's loaded in a tensile manner, and it undergoes an elongation delta with a final length of L plus delta. Shown on this slide is a concrete material expansion. A concrete is cast in early age, shown at left with a length L. As time passes, the concrete will expand, ending with a final length L plus delta. So those are the three basic characterizations. The fundamental question that I'm trying to answer is what happens when these three scenarios interact? A steel elastic behavior, a concrete elastic behavior, and a concrete material expansion. Shown in this schematic is a restraint system where two steel rods connected to a rigid top plate restrain an expansive steel column. The top plate is assumed to be rigid, that is, it undergoes no flexural or cupping displacement, but only transfers load to the steel rods. The column is expansive and will displace as it cures, shown here. Because of the restraint system, the steel rod and the columns, all three undergo the same displacement, delta, and the forces are as shown here. The steel is placed in tension and the concrete is placed in compression. In order to use this theoretical scenario to simulate a mature concrete boundary condition, axial stiffness is defined as EA over L, and the stiffness of steel is equated to the stiffness of concrete. The only unknown in this scenario, assuming mature concrete properties, is area of steel, which can then be isolated and solved. So for this calculation, the result was approximately 4 5/8-inch steel bars is equivalent to the boundary condition that would be exerted by mature concrete for this test setup. In order to bracket the problem and achieve some spread and evaluate sensitivity of the setup to change in stiffness, test frames were also constructed with 4 1/2-inch rods and 4 3/4-inch rods. So this provides a spread of basically 44% stiffer than the theoretical midpoint and 36% softer than the theoretical midpoint. Shown here is the test scenario that was used in this experiment, analogous to the primary components in the theoretical scenario that I derived on the previous slides. 4 steel rods constrain a 4-inch diameter concrete column shown in the center. The rods are placed at each corner. There's a top plate and a base plate and 2 forms of instrumentation. A load cell at the top of the column measures reaction force over time, and a geocon vibrating wire strain gauge, which I'll talk a little bit about later, is embedded in the center of the column to evaluate change in length over time as the concrete matures and cures. So drawing an analogy back from the test scenario to the in situ field scenario that's being modeled, the expansive slab that would be cast in this space is now modeled as a column, 4-inch diameter, and the reactions from mature concrete have now been modeled as steel rods. Here are the mixed designs that were used in this experiment. 4 mixed designs shown from left to right in order of decreasing percentage of component, all measurements in pounds per cubic yard. The 2 parameters highlighted in blue are constant throughout this experiment. They were not subject to change. Total cementitious material, the sum of Portland cement and component, were constant, and the water to cement ratio was not changed across these batches. Here's a basic characterization of the 4 mixes and their behavior. This was performed with a standard ASTM C878 test for restrained expansion of shrinkage comp. As you can see, they're stratified in order of increasing component, higher expansion corresponding to the maximum component amount. An additional characterization is shown here based upon unrestrained expansion. This was captured with an ASTM C157 test, still using a length comparator, but the ASTM C157 bar does not use restraint with a steel rod in the center. The instrumentation primarily used in this experiment was, as I stated earlier, geocon vibrating wire strain gauge. The strain gauge is shown at right with the interface to the wire. At left is the geocon unit with a data logger. The data logger is capable of accepting a maximum of 16 channels from 16 different gauges. And the basic principle by which the gauge operates is to electronically pluck a small wire inside the strain gauge to measure change in pitch, and change in pitch can be interpreted as change of length in microstrain as time passes. The gauge is also capable of accounting for thermal change as time passes. To determine an additional characterization for the concrete behavior, geocon vibrating wire strain gauge was embedded in a standard 6x12 cylinder. The cylinder is free to expand over time, and this was used to achieve an additional characterization shown here. This slide shows an overlay in order of decreasing percent component. And here is shown a comparison of the geocon unit to the 157 bar. 157 bar is shown in purple. These two forms of instrumentation show the same general expansion trend and shrinkage. Also shown here, comparison for a 19% component, almost identical trend on the expansion, although it's interesting to note that the geocon unit shows a less aggressive shrinkage trend after wet cure is terminated in 7 days. And a comparison for the 30% component. In addition to the additional characterization for unrestrained expansion, shown here is the instrumentation that was used to characterize restrained expansion of the shrinkage-compensating concrete. The 6x12 cylinder shown here is restrained at top and bottom with a steel plate, and a steel threaded rod is embedded in the center with a geocon vibrating wire strain gauge. The threaded rod in the center of the 6x12 was sized to be analogous to the size for a threaded rod in an 878 bar. So the reinforcement ratio for the 6x12 should be roughly equivalent to that in an 878. Here's a sample curve generated by a restrained 6x12 cylinder using 878 instrumentation, and here overlaid with ASTM-C 878 length comparator readings. The test frames used for restrained expansion with the three forms of restraint is shown here. The half-inch softest restraint is shown at left. The theoretical midpoint, 5/8 inch, is shown in the center, and 3/4 at right. The SOMAT EDAC data acquisition system used to measure load runs from the load cells at the top of each column, and the geocon data loggers are shown at left. Each column has a geocon strain gauge embedded in the center. All specimens were subject to a wet cure for the first 7 days after casting. This was achieved with a PVC pipe surrounding each column and with complete saturation since the column was filled around the outside. Shown here, after the test heads were applied with load cells, a PVC jacket surrounds each column. After 7 days, the columns are cut away. The water is drained, and the cardboard forms into which the concrete was cast are stripped away so that the columns dry completely. This graphic shows column load for the 15% from the data acquisition system measuring load from the load cell on top of each column. In general, the trend indicated is an increase in load with increasing boundary condition stiffness. So the 3/4 inch, the stiffest external restraint, generates the highest load, and proceeds down in order of decreasing stiffness. A similar trend is shown for the 17%. In this case, the half-inch rod gave the highest load. Notice, however, that in general, the 3/4 inch and the 5/8 inch rods show the same general relationship to each other as in the previous slide. And at the maximum load for 19%, maximum load occurred at 7 days just before the water cure was terminated. Once again, the curves are stratified in order of decreasing load with decreasing boundary condition stiffness, with 3/4 giving the highest load. And column load for 30% shows a similar stratification, different trend. Notice, however, that as with the three previous curves, despite the change in boundary condition stiffness, all three curves are tightly grouped. Shown here is an overlay of all four mixed designs for the half-inch restraint, and the curves stratify in order of increasing percentage of component. A similar trend is shown for the 5/8 inch columns, with the 30% giving the highest and proceeding down in order. And finally, column load for the 3/4 inch restraint, showing the same general trend, spreading out according to increasing percentage of component. This graph from the icon in the upper right-hand corner, this was captured not from a load cell, but from a geocon unit. This is expansion, change in length of the columns over time. The curves are labeled by size of rods and by the pre-compression load that was applied when the test heads were installed to measure load. Notice on this curve that the increase in expansion corresponds to decreasing rod stiffness. So the half-inch rod, the softest boundary condition, corresponds to the highest expansion, and the 3/4 inch, the stiffest, corresponds to the lowest expansion. A similar stratification is shown here in a slightly different order. Notice how tightly grouped the three curves are despite the change in stiffness. Also interesting to note that despite the fact that the 3/4 is on top, the half-inch and the 5/8 inch columns still show the correct relationship to each other, with the softer giving the higher expansion. On this curve, it's interesting to note off of the pre-compression loads, the 5/8 inch and 3/4 inch rods give the correct expansion relationships to each other, with the softer of the two giving higher expansion. The half-inch lies below the other two, and if you notice from the higher pre-compression load, from this result, it's expected that the amount of pre-compression the column receives during early age has a suppressing effect on material expansion as the columns cure. Shown here is an overlay for the mixes for half-inch restraint expansion. 30% component gives the highest expansion, followed by 19 and 15, also shown on the pre-compression loads. Similar overlay for 5/8 inch rods, with 30% giving the highest expansion and 15% the lowest. And finally, an overlay for 3/4 inch for all mixes, and a similar stratification. Some conclusions were drawn from this experiment about the instrumentation. First of all, it was observed that the geocon vibrating wire strain gauge converges consistently with ASTM standardized tests, not only the 157 but also the 878 test. Because of the electronic instrumentation, the vibrating wire strain gauge appears to generate smoother, more complete curves. This is partly due to the finer interval of readings. The minimum interval between readings for the ASTM 878 and 157 tests for this experiment was 24 hours. No readings were taken any closer together than 24 hours. The geocon unit is set to read every 15 minutes, which generates an overall better characterization due to a greater number of data points to find out what's happening between those 24-hour intervals. In addition, the 6x12 instrumented cylinders are less vulnerable to environmental variation than a standardized 878 or 157 bar. This is partly due to thermal mass. A standard bar is only 3 by 3 by 10 inches, which compared to the thermal mass of a 6x12 affects vulnerability to environmental changes. Also, due to the lower surface area to volume ratio, the 6x12 cylinders exhibit less aggressive shrinkage. This is most likely due to less aggressive desiccation after wet cure is terminated, causing the 6x12 specimens to give less aggressive shrinkage curves after wet cure. In terms of material conclusions, bracketing the stiffness problem, as I said, 1/2 inch to 5/8 to 3/4 were the three stiffnesses used, with the 5/8 being the theoretical midpoint to simulate a concrete boundary condition. This gives a change from the midpoint 44% stiffer and 36% softer. But if you notice from this curve, the theoretical midpoint is marked in red. The variation in shrinkage compensation does not correspond directly to the change in stiffness. A dramatic change in stiffness is not accompanied by a dramatic gap in shrinkage compensation, and vice versa. This leads to the conclusion that a large increase in restraint stiffness does not inhibit capability to compensate. All column expansion data sets and load data sets exhibited tight clustering despite dramatic change in boundary condition stiffness, leading to the conclusion that type K shrinkage compensating concrete is not necessarily vulnerable to applying a mature concrete boundary condition. Some additional conclusions. Compressive stress in every experiment was noted to be accompanied by significant expansion. There was no case where it was observed that compressive load or compressive stress was induced without expansion. In general, higher loads corresponded to stiffer boundary condition, and it was also observed, as I indicated in the data section, both load and expansion are influenced by the amount of pre-compression that's induced on the columns. The columns were capped with the test heads and tightened in order to maintain contact with the load cell. This necessarily induces a pre-compression on the columns, and the amount of pre-compression that results obviously has an impact on the material behavior moving forward. As a work in progress, further research will be to perform a range of tests with carefully controlled low values of pre-compression to determine sensitivity. Any questions? Yes?
Did anybody ever pour concrete in a confined area?
That was kept to a minimum. And that was not filled with water until after casting was complete. Yes?
So, would you expect any difference in the expansive characteristics if your restraint condition changes from uniaxial to multi-axial?
That's an additional further field of investigation moving forward to evaluate how uniaxial restraint influences expansion in other axes, and then from there to move on to how does multi-axial restraint influence multi-axial behavior. And that's something that's easier to investigate now because of the geocon vibrating wire capabilities that we have. It's something that wouldn't have been possible previously. Obviously, DMEC targets indicate surface behavior, and the ASTM tests only give you what the bar does. So that's something that we hope to investigate moving forward.